Good morning, everyone. So this is the problem one of IMO 2025, and it's a really interesting question, and I really love this one. And it's quite a bit easy if you strategically like divide the question and slowly read it. So first, let's read this part. A line in a plane is called sunny if it's not parallel to any of x-axis and y-axis, and the line x plus y is equals to 0. So let's first define all the non-sunny lines. So it goes like this. This is r x-axis, this is r y-axis, and the line x plus y equals to 0. Now, if you consider it this way, um, from here, it might look like this. Now, all the lines that are parallel to these lines are actually not sun. So, let's continue the question. Let n be greater than or equal to 3, be an integer. Determine all non-negative integers k such that there exist n distinct lines in the plane satisfying both of the following. For all positive integers a and b, with a plus b less than or equal to n plus 1, the point a and b is on at least one of the lines, and exactly k of n lines are sun. So let's first define what is k and n. Is k are the sunny lines, while n are the total lines. Now, the best way to approach this question is by starting with the base case. Now, like for example, since they have given us that n is greater than or equal to 3, we can like test out the n is equal to 3 for now. So, n is equal to 3. Now, they have also given us a condition that the points a plus b must be less than or equal to n plus 1. Now these a and b are the special integers due to which they are less than or equal to n plus 1. So we have to identify them, and you won't believe what happens when we identify them. Now using that equation, a plus b must be less than or equal to our n is 3, 3 plus 1 is 4. So the summation of both points must be less than or equal to 4, right? So the total points we have is 1, 2, 3. 1, 2, and 1. And that's what we have gotten. These points are actually the Gauss triangle. They make up a Gauss triangle. So the equation for the Gauss triangle is actually n into n plus 1 divided by 2. So we can say that from this we can infer that the total lines are actually n into n plus 1 divided by 2. Since we have gotten this, we can actually analyze this graph and see that that how many k of n lines are actually sunny. So there's a possibility for k is equal to 0. For example, if we analyze this, if we let all the lines to be horizontal, here k is 0. So using these lines, we can infer that k is equal to 0. But there's also a possible chance that if we tilt this line, we get k is equals to 1. So there's one sunny line over here, k is equals to 1. But what about k is equals to 2? Now if we analyze the k is equals to 2, it's incredibly like impossible to have k is equals to 2. Even if we try, like for example, n is equals to 4, we get 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. our equation for the n is equal to 4 becomes a plus b is less than or equal to 5. So the total points we have is 1, 2, 3, 4. 1, 2, 3, 1, 2, and 1. Now, if we ever want to maximize the total number of the let's first deliver the case of n is equals to 2. All right, we have to find if it is possible to get k is equals to 2. Now, if we do it like this, for example, we can't do it like this since this will be the x plus y is equals to 0, which is a non-Sunny line. So, but if we do it like this, we get k is equals to 1. Get k is equals to 2. Get k is equal to 3. And you know, as the n is progressing, we can't actually get k is equal to 2 because the total number of Sunny lines will always be 3, 1, or 0. We can even test this out later on. Now, since we got the proof that k is equal to 3, what about, will there be k is equal to 4? Now, we can also test that out as well. There can't be actually k is equal to 4. This is because if we even test that out with trial and error, we will never ever reach k is equal to 4. Now, after that is done, how can we prove that for the future n values, the answer always remains this? To do this, we can use our cheat code, which is induction. Now, in induction, we can use the geometric one, in which it's like, for example, we test the case for n minus 1, right? Now, for example, we have set the n as 4, right? N as 4. Now, to do the n as 4, we like, for example, our n was 4. Now, if you want to test the case for the previous one, first let's draw for the n is equal to 4. We get 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Alright. Now, if we consider this and we subtract 1 with it, our line actually, this one line actually disappears. Like, for example, look. 1, 2, 3, 4. 1, 2, 3, 4. Now, we get and 4 minus 1 is 3, so 1 plus 1 is 1, 2 plus 1 is 3, and 2 plus 1 is 3. Now we actually got, if we erase this line, so 4 minus 1, we get this one triangle. Now if we consider this triangle, we actually get k is equals to 1, or k is equal to 0, right? We actually get k is equal to 0 from it. So using this, we have proved that k will always be 0, 1, and 3. Thank you so much.